All right, so here we've got the last kind of chunk of calculations that we're going to be doing with buffers. And this is going to focus on finding ratios of our weak substance with its conjugate, as well as getting into the nitty-gritty of preparing a buffer and how you would make choices and how much to prepare a buffer. So, first off, calculating ratios. To calculate the acid-base ratio of the concentrations for our weak substance and its conjugate, we're always going to have a target pH that we want to prepare. And depending on which way we choose to calculate this, let me just get rid of this, we might end up with a slightly different ratio. Remember, if we use our Ka expression, which is just going to start with Ka equals our products of the dissociation of our acid over the original acid. And if we rearrange that to solve for our H plus concentration, which is helpful to us, we can use this to solve certain buffer problems, but at the same time, it's not on our AP equation sheet, so you might need to memorize it or use our Henderson-Hasselbalch. But one thing that you probably hadn't focused on that much, because we were mostly just using the Henderson-Hasselbalch equation, is that this ratio of our weak substance to its conjugate, our acid to our base component in this buffer, is actually inverted in both of them. Because of how we solve for our H plus here, we had to multiply in our K equation. In order to turn this into that, we had to multiply by HA over A, which is what ended up being multiplied by our K here. But in our Henderson-Hasselbalch, it has our A over HA. So that means that we need to be careful to specify what we solve for. College Board will take either answer, even if they ask specifically what is the ratio of acid to conjugate base. If you give them the conjugate base to acid ratio, but you specify that that's the ratio you know you've gotten, they will accept that. They're not that picky about that. You have to be worried about that in like a multiple choice type problem, perhaps, to select the right answer that follows the formatting that they want. But I'll show you how easy it is to switch between them algebraically. It's not a problem. So there are always going to be two ways to solve for these ratios. And I'm going to start each of these example problems with our kind of derived K expression equation here, because that's really what it's meant for, is meant to make our lives easier solving for these concentrations so that we don't have to do some subtraction and exponential work to solve for this log-based number here. But I'll show you both ways. You just need to get comfortable with one way or the other. It does not matter which. One you got to memorize or derive the equation, but it's a simpler algebra process. The other one, nothing to memorize. Same old Henderson-Hasselbalch. That's kind of our standard here with buffers, but then you got to do a little bit more algebra. So let's look at this first example. And once again, I'm using our H plus equation, not the Henderson-Hasselbalch. So if we're looking for our ratio of hydrofluoric acid to fluoride ion, we're looking for this ratio here. That's going to be our X. We want to figure out what the ratio would be to use hydrofluoric acid with the fluoride ion and get a pH of 3.20. Remember, we'll always have a target pH. In industry, this is going to be a pH either that we want to keep a reaction at or a certain piece of equipment at. So we have a target pH, and then we have the supplies that we're going to be using here. And the first step here for me would be go find the Ka for my given acid, and then to turn this pH into the H plus concentration that it represents. And remember, we can find the pH by taking the negative log of our H plus concentration, which means to undo that negative log, we do 10 raised to the negative of whatever our pH is. So 10 to the negative 3.20 would give me an H plus concentration of 6.31 times 10 to the negative fourth. So that's going to be what I plug in for my H plus. I've got my Ka, and then that's going to be everything I need to plug in to solve for x. So I just have a number equals another number times x, which means I'm going to be dividing that 6.31 e negative 4 by 7.20 e negative 4. And then that means that x is going to be about 0.8763. And remember, this x is our ratio. So this is our final answer. This is our ratio of HA to A minus. Write it just like it's written in our expression up above. You don't have to write it in words. But that ratio is equal to 0.876 in our 3 sig fig answer here. Like I said, pretty simple algebra to plug in these numbers. Just have to solve for that H plus number first from your pH and then go from there. That is our final answer. Now, if we're solving the exact same problem using our Henderson-Hasselbalch, which will kind of be your default, especially when you're nervous and stressed out and rushed on the test, this is going to be what you come back to for buffers. We've got our Ka for our hydrofluoric acid. This time we don't have to find the H plus concentration because our Henderson-Hasselbalch has pH built into it. As we plug in our numbers here, we're going to take that 3.20 pH equals our pKa, which remember is the negative log of the Ka value that we've got for HF, plus the log of x. So here I would just kind of simplify, take a second to do this negative log and figure out what that equals. That kind of simplifies that equation a little bit, makes it easier to see how to solve for x. I would isolate the numbers on one side of my equation, so I'm going to subtract that 3.14 from both sides, and that tells me that 0.06 is equal to the log of x. And in order to undo a log, just like how we undo our pH, we do 10 raised to that power. This time it's not 10 raised to the negative power because that wasn't a negative log that we were taking, it's just a regular log. So just 10 raised to the power of 0.06 is going to be 1.148 with some more numbers there, which technically we should round to 1 sig fig here. So technically that would mean x equals 1. I am going to keep a couple more digits here just to kind of keep things similar because I do want to compare these two processes to each other, which means keeping 3 sig figs here will make things a little easier to compare, even if mathematically I should be keeping 1. Not a huge difference in the long run, and we'll see an example of this a little bit later, where I take it a step farther into the preparation, and there's no difference when it comes to the final answer. Now, you might notice this is a different number than, as my final answer here for my ratio, than with my previous calculation, but that's because this is the opposite ratio. This is technically my conjugate base to acid ratio instead of my acid to conjugate base ratio. And I'm going to go ahead and put these side by side just so we can compare them. You can definitely see there's more algebra, more work involved in that second method than the first. And in order to compare these answers, to take the inverse to find the opposite, the reciprocal of this fraction, this ratio that we've been looking at, we would just need to do 1 over that fraction to flip it, which means we would just have to do 1 over these numbers here in order to figure out what they would be if it was talking about the opposite ratio, which when we do that ends up being pretty similar to these values. There is a little bit of a difference. It is not perfect, but it is pretty similar. And if you show your work along the way, they're not going to mind that little bit of inconsistency in the answer because, but I've told you before, I doubt that they're going to be doing any kind of sig fig point, because remember, they only get to choose one place to make the sig fig point in that exam, and I doubt it's going to be one of these processes where there's multiple ways that end up with different sig fig requirements and lots of opportunities for mistakes. That just makes their grading harder. So, hopefully this isn't too bad of a process, and like I said, you can choose whichever way you'd like to work these out. I am going to do it both ways for this next example as well, but then I am eventually going to just start doing it this way, which is easier and quicker to go through this process to find these answers, and gives me more sig figs, so a more reliable answer. So that's going to be the way that I choose in the long run. But you do you, whatever works with you, the calculator you have, and kind of how much you're prepared to be carrying in your head with you into that exam. So example number 9, I've got my 2 different methods set up here. I'm just going to work them on the same slide this time. Once again, I'm going to need to start by finding the Ka value that goes with this propanoic acid. And for this first method, I am going to have to find my H plus concentration by doing 10 to the negative 5.20, taking 10 to the negative of my target pH here for my buffer system. And then if I plug those 2 numbers in together to that H plus equation, H plus is equal to Ka times my ratio, which is my X here. Divide in order to find X, and then that gets me that my acid to conjugate base ratio will be 0.485. If I go over to my Henderson-Hasselbalch equation, I can plug in my target pH equals the negative log of my Ka value plus the log of that ratio. Once again, taking that negative log of my Ka value just to find that number, subtracting that number from both sides, and then I get a number equals log of my ratio. And so to find that ratio, to find my X, and undo that log that it's in, I do 10 raised to that power, and 10 to the 0.31 is 2.0417. So here my conjugate to weak acid ratio is 2.04. And just double checking, you do not have to find the other ratio there. There's no reason to do both, but just to reassure you that even though they are different numbers, they do end up correlating pretty closely with each other. It doesn't matter which way you do it. It will always end up getting you credit as long as you're careful for what they're asking for. Labeling your answer, really, what it comes down to. So here, example number 10. This question doesn't actually ask for the ratio. It asks you to find how many grams of our conjugate, grams of potassium cyanide, I'd need to dissolve into a certain amount of my hydrocyanic acid to create a buffer solution, with my target pH being 9.10. So it doesn't say to find the ratio, but that's what we need. We know how much of our weak acid we've got. We're going to use the ratio that we solve for in order to figure out how much of our conjugate we need to put in there. And this is kind of a stepping stone into that next page, page 7, where we're going to get into the nitty-gritty of how to calculate the numbers we need to figure out how to prepare a certain buffer solution. There'll be some extra steps there, putting it all together, but this is really that stepping stone, taking it one step farther from just finding the ratio to using that ratio to find the amount of one of our substances. So if we start this process off the same way again, finding our Ka and our H plus value from our given values here in the problem, we can set that up with our H plus equation, saying H plus equals Ka times our ratio. Divide in order to find our ratio is 1.28. And then this point, we would need to, this 0.05 number, I didn't actually show my work very well for. This is the amount of the acid that they told us about in the problem. And what I did here is I turned my milliliters into liters by moving my decimal 3 times to the left, and then I multiplied that by its molarity, and 0.5 times 1 is 0.5, and that would keep 2 sig figs there because of my molarity. So that's how much of my weak acid I have. So I've just plugged that information into this ratio that we've been finding, and now I can solve for that conjugate A minus value, because I know that the 0.5 over that conjugate value has to equal 1.28. So at this point, this means X, and this time my X is my amount of conjugate, would be about 0.3906. Now, we need to turn these moles of conjugate into grams, but I want to go ahead and do our Henderson-Hasselbalch method real quick over on the other side so that we can calculate those grams at the same time for both. So here, once again, I'm taking my pH equals the negative log of my Ka value plus the log of x. Simplifying that down by taking the negative log of the Ka value, subtracting 9.21 from each side gives me negative 0.11 equals the log of my ratio, the log of x, and then doing 10 raised to that power in order to solve for my x. And that tells us that my conjugate to acid ratio is 0.776. And once again, if I plug in my acid moles, once again, those square brackets mean molarity technically, but as long as they're the same solution, they're all in one solution, so the volume is equal, so the moles are equivalent to dividing those molarities. This time I'm just plugging in that 0.50 moles on the bottom where our acid is, solving for the x on top, which is a little bit simpler, just have to multiply by 0.5, and that gets me that my moles of conjugate would be 0.388, which is not identical to my number from using my H plus equation, but once we round these to 2 sig figs, which we should in both situations because that's our moles, has the least number of sig figs, has 2, then either way we're doing 0.39 moles, turning that into grams of our potassium cyanide that it's specified there by multiplying by that molar mass, and either way we do it, we get 25.4 grams of potassium cyanide. So that is our final answer, and it is the same no matter which method we use, even though there are some slight variations in the numbers that we're getting and how they would relate to each other. There's no significant difference when it comes to the preparation of a solution. So, like I said, this is our stepping stone. We would be solving 25.4 grams of potassium cyanide into that 500 milliliters that it's specified up here. And once we do that, we would have our buffer solution at 9.10 pH. So let's go into a little more detail on this next page about how we would do this kind of from scratch. But it's basically going to be like what we're doing here in this problem. So, putting it all together, preparing buffer solutions. Get that cleared off there. I've mentioned this before, and here is when it really becomes important, that when preparing a buffer, the best buffer solutions will have a ratio of acid to conjugate or acid to base, no matter which one is our weak in our conjugate, that is close to 1:1. And that's going to help it equally handle changes in pH up and down, acids and bases being added or present in that buffer. And we always want to protect from both. Of course, we also want a large buffer capacity if we can, but oftentimes we're limited by the solutions that we have present and the materials that we have present. But no matter what, a better buffer will have a ratio closer to 1:1. And that's not always possible, but we'll do the best that we can. The simplest way to design a buffer solution at a specific pH, because remember, we're always going to have a target pH that we're wanting to keep our reaction or our equipment at, is to choose an acid that has a Ka value that has a Ka with an exponent that is close to the desired pH. And that's a really important statement there. And we've already kind of talked about that a little bit as well. I know it was kind of an offhand comment, not everyone was necessarily paying attention, but we talked about how when that ratio of our acid to base here is 1, we're taking the log of 1 here, and the log of 1 is equal to 0, which means that that whole term there that we're adding to our pKa is 0, which means when we have that best ratio 1:1, our pH of our buffer is going to be equal to the pKa of our weak substance, our weak acid that is part of our buffer solution. So that's what our target is, and the closer we can get our exponent to our pKa, then the better that, to our pH, to our pKa, then the better our buffer can be. and the closer that ratio will be to 1. So, this is an example. Doesn't go into any calculations, or at least not in-depth calculations. We just need to figure out which substance we want to use for a buffer. We need a buffer at pH equals 4.3. We can choose from these specific acids and their conjugate. Which would work best? Well, we can look at those exponents and probably eliminate, since our target is 4.3, the exponent here on hypochlorous acid is just way too big. The rest of them are pretty close to 4 though, and if you forget your negative log rules, how to do those in your head, then it might be a little bit hard to figure out which one is the best. So it's not that hard, doesn't take that long to find those pKa values. Just take the negative log of each of these numbers, which does once again confirm that our answer choice D is just way off. But then if we look at each of these compared to our target pH of 4.3, then 4.19 is the closest that we can get to 4.3 here, which means benzoic acid is the best choice for this buffer. And our ratio won't be exactly 1 because our pH isn't exactly the same as that pKa, but it's going to be the closest it can be compared to all of these other options. So, like that bullet point says, when we can't get the perfect acid for that specific pH buffer, we'll use the closest one and then fine-tune the pH with the ratio of the weak acid base and its salt. And that's like what we were doing on the previous page. And that's basically what we're going to be doing down below. So we have this blurb that reminds us that most of the time when we need to make a buffer solution, we know two things. The buffer's pH, of course, and the volume of the final buffer solution that you need. You'll know whether you need 500 ml reaction or 1,000 ml reaction, so you'll know about how much buffer you need to make, and you can always round up to make a little extra there. Or you need your pH probes to each be in a 100 milliliter sample of a buffer solution so that they don't get ruined. So oh, I have 10 probes and they each need this much. You'll know how much buffer solution you need to make. So pH and volume are the two things you'll generally know. And that's the only information I've given you in the problems below. And we need to figure out and describe how to make the best possible buffer solution for each of those situations, only given the options in the table of chemicals below. So we're going to go through a process that's basically the same as what we were doing on the previous page. First, we're going to use the given pH to determine the pair, just like we did in the problem above, to figure out the right pair that's going to give us the best possible acid-base ratio, the one where the pH is closest to the pKa. And then we're going to use that given pair to calculate the acid-base ratio, using the Ka for that specific weak substance. Find the ratio needed to reach that given pH with that pair. So that's exactly what we were doing on the previous page. This next step is technically one of the only new calculations we've got to do here. We're going to use the given volume, because once again we'll know the volume we're aiming for, and once we know what acid we're going to be using and what molarity is available for it, we can use that volume and molarity to calculate the moles of that weak acid that we're going to have. And once we know those moles, then we can use those moles in step 4 with the ratio we already solved for to find the moles of our conjugate needed and convert to grams, just like we did in that last problem on the page 6. And that's technically all our calculations. At that point, we're just going to put it all together into a statement. I've given you kind of this structure, which just has us tell a specific amount of our salt getting dissolved into a specific amount of our solution. So it's just very formulaic, very basic, but that's what we're solving for, is certain amounts of a certain salt, certain amounts of a certain solution. So really just one new calculation, and then I guess, summarizing it all together. But it shouldn't be too much worse than what we were doing on that previous page. So let's go ahead and look at each of these problems and try and figure out first just which pair do we need to use for each, just so we know what information we've got and what we're working with. And in order to do that, just like what we did in that problem up above, we should probably find our pKa values. So I've already done that for us here for the first 3 pairs, but you'll notice pair number 4, ammonia, has a Kb value, not a Ka value. So we can't just take the negative log of that. That'll give us the pKb, which is not part of our Henderson-Hasselbalch, is not going to be equivalent to the pH of our buffer. So first we have to turn that into our Ka value. Remember that we're going to do that by taking our Kw value, 1e negative 14, and divide it by our Kb value. And when we do that, and we have our Ka, now we can take the negative log of that, and that will get us our pKa, which, there it is 9.25. So, looking at our first buffer solution, we want our pH to be about 4.3, and at first glance you might think that pair number 2 would be the best. That's 0.59 off. But pair number 1 is actually very slightly closer. It's 0.56 off and away from our pH. And it is a very small difference. And if you'd like, we can go through the process that would be needed to use pair number 2. It'd probably be pretty similar. But pair number 1 is the closest, which means our ratio of acid to conjugate will be closer to 1, and it's going to make a slightly better buffer here. So we are going to use pair 1 in the calculations that I do here. And then for a pH of 8.7, it's not even close. That's definitely going to be pair number 4 as our best choice there. If it would please come up. There we go. So that's the information we need to focus on. Honestly, we don't care about anything it talked about with pair 2 or 3 here for these 2 problems. So in these next couple slides, I'm just going to take the information we need along with a question so that we can kind of clean things up and stay focused on what we need. So here, our whole goal is to describe how to make 100 milliliters of a solution buffered at pH 4.3 with this specific formic acid and sodium formate. So step number 1 is done. We've chosen the correct pair, which means step number 2, we need to figure out what our ratio is, and I'm just going to use our H plus equation. I'm not going to do it both ways this time because that's just going to get a little bit too crazy, too redundant. If you solve it using the Henderson-Hasselbalch equation, go for it. Tell me how different your numbers turn out, because I'm sure it's just going to be a little decimal along the way that might be different, but we'll see. So for my H plus equation, I do need my H plus value in addition to the Ka that I've already got, that 1.80, E negative 4. So remember that our H plus is equal to the Ka times our ratio, which means my next step is just dividing those 2 numbers to find my ratio, which here would be 0.278. Now that I have my ratio, I need to plug in the moles that I know to find the moles that I don't know. And because we know we want to make 100 milliliters of our solution, and my materials, I only have 0.1 molar formic acid, that 100 milliliters and that 0.1 molar, of course changing my milliliters into liters to get moles, is going to give me 0.0100 moles of my acid. So if I can plug that into my ratio, got my acid over the X, which is the amount of conjugate that I'm going to be finding or needing here, equal to my 0.278 ratio. That tells me that I'm going to need 0.360 moles of my conjugate. And because I was given my formula mass of my sodium formate, I can use dimensional analysis to turn those moles into grams, and that tells me I need 2.45 grams of my sodium formate in this buffer solution. So basically everything is the same as what we did in that last problem. We just had to do one extra little step here to find the moles of one of our substances because we didn't know which of our acids we were going to be using here in this problem. And now that we've got all that information, we just kind of have to plug it into that structure that I gave you. we're going to be dissolving 2.45 grams of that sodium formate into 100 milliliters of the 0.1 molar formic acid. Oop, that says sodium formate again. Huh. Let's fix that. There we go, a little bit better. So, just finding our ratio, using the ratio to find moles, and then turning moles into grams. So, let's do another example. Example 13, remember we're using pair 4, and I did include that Ka value that we had solved for. We don't need the pKa anymore, but this Ka value will be useful to us in general. And first step is the same. If I'm using my H plus equation, I've got to find my H plus concentration. Then I can set that equal to my Ka times my ratio. Divide to find that ratio is 3.597 or 3.60. There's an extra 0 there. Little bitty. So if my acid to conjugate ratio is 3.6, I can now use my volume, my 200 milliliters, as well as the 0.4 molar ammonia that I have access to, and multiply those together in order to find the number of moles that I am going to have of my weak acid, actually my weak base here. And then I'm solving for my conjugate. There we go. Because this is a weak base here, we need to make sure we're still plugging this in for the base component, not just in the HA, because we always plug it in for HA. This is a weak base, so it's the basic component, and our conjugate is the conjugate acid. So that is what we're solving for here. We want to find the amount of our acid that we need to add to this weak base. It's just the salt this time instead of the solution. Let me erase some of this stuff here. So, solving for that x, we get 0.288, and that's the perfect number of sig figs for us to plug in. Multiply by that molar mass of our ammonium chloride, gets us 15.1 grams. And then putting it all together into our structured response, and you can say this in a different order in different ways as long as you get all this information in it. But we're going to dissolve that 15.1 grams of our ammonium chloride into the 200 milliliters of our 0.4 molar ammonia solution. And that is how we would make our buffer at 8.7 if we needed 200 milliliters of it. So hopefully that's really not too bad. There's a lot of little details, but it really just comes down to doing that algebra, solving with the equation of your choice, and making sure you can remember the type of information you need to make a buffer. The amount of your acid and conjugate, or your base and its conjugate. But that's it.